We all know that Sun is the nearest star to the Earth. It is a massive ball of gas clouds, and it controls all the activity on the Earth, life itself. So it is a very important object to mankind, and it is important to know what goes on in the Sun. The interesting thing about Sun is that because it is the nearest star, it is the one which we can study in great detail. There is hardly any other object nearby which you can look at with such a high resolution. In the context of the activities which go on in the Sun, we have been trying to understand in the last several decades those kinds of things which are of great relevance to us. This year we have organized an international colloquium where a large number of participants have come from all over the world to the city of Pune, and the National Center for Radio Astrophysics has organized an International Astronomical Union colloquium named Solar and Interplanetary Transients. In the context of this colloquium, we are happy to have with us today Dr. Ernest Hildner, Director of the Space Environmental Lab in Boulder, Colorado. We also have the great pleasure of having Dr. Murray Dreyer, who is a Senior Scientist of the Space Environmental Laboratory. Can you first of all tell for our audience what is it that makes Sun erupt, or how do things happen from the Sun which affect us on the Earth?
The Sun is a very ordinary star, but it's our star, and it has a magnetic field which gets generated by processes we don't understand, so that the field is greatest every 11 years and then fades away to a minimum and then comes back up to a maximum. This magnetic field evidently is the cause of the eruptions of solar atmosphere that we see, and when these eruptions come out from the Sun, should Earth happen to be in their way, then they hit the Earth's magnetic field and they create things like the northern lights and the southern lights. But more importantly, they affect communications, they affect radio navigation, they affect power lines, they affect astronauts if they are flying around in space outside the space shuttle. And so there are a variety of technological systems that are affected by these outbursts from the Sun.
Could we compare what happens on the Sun to something like a volcano on the Earth? You know, these volcanoes activities increase and then they burst out, and then we have all these lava flows.
That's an analogy that might be appropriate only to, say, a first level of understanding. The volcano is a sudden eruption, a release of energy with the spewing out of volcanic material that you mentioned. So I would prefer to think of these activities on the Sun in a little different way. As Ernie mentioned, the magnetic field control the plasma, the ionized gas,
Yes.
consisting primarily of protons and electrons that are taught in basic physics courses. This basic gas, this plasma, is constantly moving away from the Sun in all directions throughout the solar system, forming what is called a heliosphere.
You mean the Sun cannot hold on to those protons and
In
electrons?
some cases, the magnetic field is not strong enough to hold the plasma, where the magnetic field lines are able to open out into interplanetary space. This is where the plasma escapes as the solar wind. And so that's always been an attractive matter to me, because it's almost like a giant wind tunnel, which is where I had some of my early training.
Yes.
And so when these eruptions take place, they spew out whatever eruptions they are, no matter how they occur, either suddenly or perhaps gradually. They spew out disturbances. Sometimes some of these disturbances may be called ejections or due to the eruptions, and they perhaps can cause shock waves that propagate through this heliosphere. And as Ernie mentioned, some of these disturbances can impact upon the Earth, causing the disturbances in the Earth's environment that affect mankind in very subtle ways.
Now, how long does it take for these to travel from the sun to the Earth?
Normally, the solar wind takes about 4 days if nothing happens on the sun. A normal solar wind takes about 4 days, moving at about 400 kilometers per second to reach the Earth. If a disturbance takes place on the sun, it could take 3 days, 2 days, maybe perhaps in some cases even 1 day. And we would like to have an advance warning as much as possible.
I see. Yeah, Ernie mentioned a little while ago that the satellites will be affected, and even the astronauts will be affected because these particles come from the sun to the Earth. Is it that they are very energetic particles that you will be, if you cannot be hit by them and you will get
That's exactly right. It would be like carrying a piece of radioactive material around with you. The sun makes particles at special times. It makes particles that are so energetic that they can cause cancer or cataracts in your eyes if you're exposed to them. At the worst of cases, an astronaut outside the Earth's magnetic field, perhaps on the surface of the moon or something, could in 1 hour get a fatal dose.
I see. So that's pretty dangerous.
Well, it's dangerous, but it's rare. It's dangerous when it happens.
Okay, but is there an altitude which you would say is sort of the threshold altitude beyond which you have to be much more careful?
Quite right. I should not be frightening people watching this program, because the air under which we live and which we breathe protects us against these particles that are coming down from above, as does Earth's magnetic field. These individual charged particles cannot penetrate the Earth's magnetic field very effectively, and consequently one has to go up to astronaut altitudes before there's any significant effect. People walking around here are perfectly safe.
Are perfectly safe.
Yes.
But you also mentioned that I think either here you mentioned about all these communication blackouts which take place as a result of this. If there is a magnetic shield around the Earth, how is it that these particles still penetrate and come inside?
These energetic particles that Ernie referred to can come either directly from the sun, or they may even be generated by the shock waves that are propagating out from a disturbance. And these particles enter the polar caps, northern and southern polar caps, and can affect the ionosphere, changing the amount of electrons in the ionosphere. The ionosphere, of course, acts as a guide for radio communications.
Yes.
And so if that level of the ionospheric layer is changing with height, or in the capability to absorb reflecting radio waves, then you may or you may not get the radio signals, radio and TV signals.
But these days of all kinds of high-tech things, you have coaxial cables and you have optical fibers for communication, all that. Is there a real problem if we don't have this HF communication?
It's that half the world's communications are at HF, high frequency, which travels between the surface of the Earth and this ionized layer that is affected. And if that layer, upper layer, begins to ripple like this, then the waves don't go through that gap very well. So half the world's communications. Sending a high frequency signal up to a satellite right through the layer, it's unaffected.
That is unaffected.
Unaffected.
I see. And you also mentioned, Ernie, about power line blackouts and all that. Can these particles produce power line blackouts? How does it happen?
The Earth and its magnetic field are actually embedded in the solar atmosphere. As Murray said, there is a continual outflow from the sun which distorts the Earth's magnetic field. The pressure of this solar wind, the hot atmosphere from the sun coming out, blunts the magnetic field on the front side of the Earth and drags it into a long tail downstream.
Yes.
But then when there is a gust of particles in the solar wind, there is increased pressure and the Earth's magnetic field changes shape, and currents have to flow to make that happen. The change in the magnetic field of the Earth induces a current, geomagnetically induced current is what it's called, in the long transmission lines that are long conductors carrying the electric power, and those power lines shut themselves down because they see a voltage on that line that's not supposed to be there. This is more, I should say, this is more effective or more dangerous in high northern and southern latitudes than it is near the equator.
So, if that is the case, then it becomes very important to be able to predict the arrival of these.
Yes, indeed.
These things. What is the kind of advance notice that one needs?
We can hardly give any advance notice at all. We make predictions for a day in advance,
Yes.
but those predictions are not very accurate because we don't know enough about the sun, which is one reason why you organized this colloquium. But soon we will have a spacecraft which is in orbit at a point where the pull towards the sun is balanced by the pull towards the Earth, and the spacecraft will just stay there. So everything coming out from the sun will wash over that spacecraft 1 hour before it hits Earth. We can radio down from that spacecraft in almost no time at all at the speed of light, and therefore we will be able to give 1 hour notice to the power companies.
Okay, this spacecraft is located very close to the Earth, right?
About 1.5 million kilometers, 1% of the way toward the sun.
Towards the sun.
Yes, it's a long way away.
Okay, so you have this big gap between the sun and even this spacecraft.
99% of the distance from the sun to the Earth, yes.
So, is there, Murray, can you just enlighten us on whether there are any other ways in which we can get information in sufficiently advanced time, which will help us?
In principle, it would be lovely to have an armada of spacecraft between Earth and the sun
At various distances.
At various distances, and moving around the sun and looking
Yes.
looking at the solar wind and what's happening as a function of time, at disturbances that propagate from the sun to the Earth. But that is obviously a pipe dream because of the cost.
Very expensive.
Very expensive, and therefore.
Yes.
One of the main reasons why so many people came to this meeting, I believe, is because of the strong remote sensing capability that exists here in Pune at your institute, because of the UTI radio telescope that can do radio map imaging of the disturbances that propagate away from the sun in all directions through the heliosphere.
Okay.
And that's one way of observing techniques. Another way is doing computer modeling, the way the Weather Service uses it, and a start has been made in that direction in various groups in several countries, and not only the United States but also in Russia and China, Czech Republic, and so on.
We have started calling this as the space weather, right? Because we are trying to predict the weather between the sun and the Earth, what is happening in the intermediate space. And I was reading the other day that this space weather prediction, we are almost about 50 years behind in comparison to the meteorological weather prediction. Would that be a correct statement, or do you think is
I happen to think it's a very close estimate, because the people in the weather business have had a long history of from where they started to where they are today, so that we could see what's coming up in the weather by just turning on the TV channel.
Yes.
And I hope someday we can do that with the space weather. I hope.
That is the day when we would be probably flying from United States to India in about 20 minutes or something like that, right?
Cheaply.
Cheaply, yes.
And also picking up a cellular telephone and calling to the United States.
Yes.
And of course, our big worry is that the armada of Earth-orbiting spacecraft might interfere with the radio astronomy, which will give us the remote sensing.
That has been a great big worry.
Yes.
Thank you, gentlemen, for being with us today and telling us a little bit about what happens between the sun and the earth and how it comes about and all that. Thank you.
Great pleasure.
Great pleasure, Anand. Thank you.